We're looking at question 2. It says that Alice drops a rock into a well and she hears the splash of that rock 4.1 seconds later. The speed of sound is 331 meters per second, and it also tells you it wants to know how deep the well is. So let's think about what's going on. So it says Alice drops a rock. So the rock has to travel down the well. Okay. Then the rock hits the water, makes a splash noise, and then the sound wave has to travel back up until Alice can hear it. We know that whole thing takes 4.1 seconds. So let's look at that. So we know the rock has to travel downward a certain distance. That's the depth of the well. And then once the rock hits the bottom where the water is, the sound wave has to travel back up the same distance so that the sound wave will hit Alice's ear. So we're going to need two distance formulas. So for sound, there goes our formula. We know that this sound wave has to travel upward, however deep the well is, okay, in a certain amount of time. Now the rock, on the other hand, has this formula. And that's because the rock is falling due to gravity. Gravity is causing the rock to fall. These d values are the same because it's the same well. The distance the rock falls will be the same distance the same distance the sound wave has to travel back up. Okay, so let's start thinking about things we know. Let's talk about the rock traveling downward first. So the rock traveling downward. Well, I have my rock. I'm gonna drop it. Ask yourself, what's the initial speed of the rock? Well, it's 0. We also know A. A in this case is gravity, so 9.8. But we don't know how long it takes for the rock to fall that distance. We don't know the time. We know the total time, but we don't know the time it takes for the rock to fall that distance. So that's the formula that we have. We could simplify this a bit. Let's get rid of this. Now we're just dealing with this portion right here. Okay. Now let's talk about the sound wave. The sound wave has to travel up the same distance. So keep in mind, this d and this d are the same. We know the speed of sound. The t is the tricky part. We don't know how long it takes for the sound wave to travel back up, but we do know that the total time is 4.1 seconds. So 4.1 minus the time that it took to fall will be our time here. So let me say that again, because that part is the tricky part, I think. These two t's are different. The time it takes for the rock to fall and hit the bottom of the well is different from the time that it takes for the sound wave to travel back up that same distance. So really, I probably should have labeled these T1 and T2. That probably would have made my life easier. Okay? Because they're different. The time that it takes for the rock to fall down is probably a lot longer than it took for the sound wave to travel back up the same distance. Okay, so those two times are different. Let's say, and this is just supposing, let's say T1 is 3. That would mean T2 would have to be 4.1 minus 3. Because the total time is 4.1. So whatever time we get here, 4.1 minus that time will tell us the time it took for the sound wave to go up. So thinking that out, I just did 4.1 minus t. So these are both T1s. So here's your formula. You have the speed of sound. You now have 4.1 minus T1. Here you have D equals 4.9 T squared. Again, this is T1. So now I have two formulas. Both of these D's are the same number. Both of these T's are the same number. Set the two equations equal to each other. Solve for time. That'll help you get to the depth of the well. It's going to be a system of equations. You may have to use the quadratic formula, but here's the setup. You have two equations. Here's equation 1, here's equation 2, and both equations have the same variables. These D's are the same, these T's are the same. Solve for one of the variables. It'll help you get closer to the depth of the well. It's going to be a system of equations. You're probably going to have to use a quadratic formula.